Morning people, welcome back to the next lesson, and the next lesson is the next topic. And if you looked at your learner guide, you will see that it is stress and strain. Okay, now people, now stress and strain isn't a massive chapter. It's more like an introduction. You take it further as you go up the levels, and as if you think back to my first talk, my introductory talk for TOS, I did say that there are 3 topics that we take from applied mechanics and we sort of expand on them in a big way, and there are other topics that will be new. This is the first new topic in TOS that you will doing. Okay, it's called stress and strain. Now people, now if you go to Blackboard, you will see I put a document there, a PDF document called Core Notes. Okay, there's the chapter. I didn't put this note together, I just put it there for those who want to read it. You should read it to add to what I was saying. It's called stresses and strains, which I don't really fully agree with. It should rather be stress and strain. Okay, but that's a small thing. It's on page 2.1. Okay, so that's chapter 2 of that note. So it's called stress and strain. I've also added another note myself, just 2-3 pages, nothing major, that I'm going to be working from. It's called direct stress and strain, and it's the same thing. So I'm just adding to it. So read the 2 in conjunction with each other. Okay. Now people, now imagine if we take, say, let's say we take a piece of wire. You know what a wire is? If I can draw a small piece of wire like so, and let's say it's 3 millimeter diameter. Okay, very thin. Okay, and I put it into a machine and I apply a tensile load to it. What is tensile load? Yes, you got it right. That means I'm stretching it. Okay, we can't compress a wire. Why can't we compress a wire? Because it'll just bend. It'll be meaningless. Okay, so let's say we take a piece of wire and we stretch it. Okay, we hold the ends tightly, and then we apply the tensile load, and then we apply a little bit more and a little bit more. Okay, can you think in your mind what could be happening? Okay, now as you apply the tensile load, this length of the wire here, if I could do this, maybe just roughly like so. If I can call it L for length, okay, whatever it might be, 200 millimeters, 2 meters. Okay, and if I put it in a machine and I hold it tightly at the ends and apply tensile load, the wire is going to get a little bit longer, just a touch longer. Okay, and if I apply a bit more tensile load, what's going to happen? And when I say bit, I mean just a tiny bit. It will get a little bit longer, and as it gets longer, the length that it extends by extends. Okay, that extends by is so small you can't almost see it. So tiny, it's like fractions of a millimeter. Okay, and I think you can see where I'm going with this. As we apply the tensile load, the wire gets longer and longer and longer for small amounts. But if we continue to apply the tensile load to the wire, what's going to happen to the wire? Yes, a lot of people would say it will snap. So no, snap isn't nice. It isn't a nice structural word. The word is it will fracture. And I think I watched a movie the other day, some months ago, called Fracture. A nice movie, but scary, but there you go. It will fracture. Okay, so if, let's say it fractures in the middle there, it will look something like so. Let's say there's a wire, it will do something like so. It will get thinner. It will get thinner like so. And it will fracture in the middle there. It will just break and it will fail. Okay, now, but why do we want to know all of this about materials? Why do we want to know when it's going to fail? I think you can guess it. We want to be able to stress out, like we stress you in exams. We want to be able to stress out the material so much so that we want to know just before it fails that we can stress it out to its maximum capability without it failing. Why do we want to do that? It's because we want to put in as little material possible into structure so that the structure stands throughout its working life without failing. Okay, because if a structure fails, let's say we have a massive steel building. Let's say I got a steel building over there like so, and I got another one like so. Let's say it's a factory, a steel factory like so. Okay, and the building is made up of like so with, by the way, that's 2 columns, that's 2 rafters, columns. I'm just making quick notes here. Columns and rafters. You should actually know these terms by now, I think. That's columns, that's rafters, okay? And that whole thing together there is called a portal frame. Portal frame. Okay, portal frame. And there's purlins running across it, like so there. Okay, that's the whole building. Just very briefly, okay. So we want to see how much load we can put on this building, on the, let's say it's a steel building, okay. But we want to make the building as light as possible. And when we say light, we don't necessarily mean light in terms of weight or mass. We mean the smallest sections possible. So if it's an I section for columns, we want to put the smallest ones in, okay. If it's for purlins here, these members running across the room is called purlins. We normally use steel angles like we did in section properties, or we can use what we call lipped channels. Yeah? Lipped channels. When I say lipped, it means we take a plate. Let's say we take a 3mm plate like so, 3mm plate, and we bend it 1, 2, 3, 4. We make 4 bends in it, and we turn it into a lipped channel. Okay, so we want to make the building as light as possible, and as I said there, not necessarily light as in mass or in weight, but we want to make the sections as small and as thin as possible. Okay, why? Because money makes the world go round, yes. Okay, we want to put the lightest building, which will cost us the least, so that the builders can make the most money, or whoever's all in part of the contract. Okay, so we want to know how much we can stress the building, how much load it can take before it fails. Because if the building fails, if this building fails, and let me take a blue man, and let's say I'm standing inside like so there, and the building fails. If it's your brother or sister, what happens? The building falls down, and if there's people inside there, they could get hurt or they could get killed. And that is just absolutely bad news. Okay, so we want to know how to stress a structure, okay, and how much load it can take before it fails, so that it's safe throughout the working life of the structure. Okay, now people, now that's a basic introduction. Now if let me just clean this board quickly here. People, there's a wire again. I just quickly clean up the board for us. There's a wire. So let's say, as we stress out the wire, it's in a machine, and then we record. Maybe I should make it F rather. Make it F, yeah. Tensile F, same thing. Okay. So let's just say that as we apply the load, we record how much this wire extends by. So let's say I draw a graph. So here's my graph. Oops, that's nasty. Okay, and let's say on the vertical scale, I record my force in kilonewtons. Okay, and I record my extension in millimeters, that's kilonewtons. Okay, and let's say we did that. Okay, we apply the load and we recorded the extension. Okay, let's say force load. And there's that makes a dot. Okay, so much force, so much extension. Okay, now remember the extension is very, very tiny. Right, then we increase the force by a particular amount, and we measure the extension, and we plot that point. Okay, and then we increase the force by a similar amount, and we record the extension again. And we continue, and we continue. Okay, and we do that up until the point before the wire fractures. Okay, and then we plot that graph, and you can see, I think you can see what the graph is going to look like. Yes, it's going to be a pretty much a straight line going up from left to right. What does it mean? It means that as the force gets bigger, the extension gets bigger by a similar or same amount. Okay, these two vary with each other directly proportionately. Okay, the one gets bigger by a similar amount as the other one gets bigger. Okay, so but also, and we also found there that when we did further tests and we drew a stress strain diagram, there's stress, and by the way, we'll talk about this more. I'm just doing introduction now. There's stress and there's strain. Okay, I'll talk about this later. If we draw a stress strain diagram, we see there that up to the point before the wire fractures, it also increases, the one also increases directly proportionately with the other one. Okay, now in the note that I gave you, there's my note there. If I go down, I think there was 3 or 4 pages. If I go down to the last page there, there's the stress strain diagram that I'm talking about. Okay. Right, notice there's my straight line that I'm talking about. There's my straight line there. Okay. And it goes up to there, up to the limit of proportionality. Now, what do you think that means? Now, remember we said earlier that as we stretch the wire, we stretch it more, and then it starts to stretch permanently, then it fractures. And if we recorded that parts of the behavior of the failure of the wire, we get the graph doing this here. Okay, that means proportionality. That means from there to there, as the stress gets bigger, the strain gets bigger. There's the symbol for strain. There's a symbol for stress, symbol for strain. Okay, but as up to this point about here, as the stress gets bigger, the strain gets bigger by the same amount. But of course, at this point here, the wire starts to fracture permanently. It will not come back to its original shape. And as we go further, it says plastic ultimate or maximum stress, stress at failure. So by the time we get to this area, the wire has broken into 2 bits. Okay, and of course, this is where we don't want to be, because this is where the building is going to fall on you and kill you. Okay, so we want to stress out a material, be it steel, be it concrete, be it timber, be it whatever. We want to stress it out to this point over here, to its limit of proportionality. Why do we want to do that? Okay, because if we get to this point here, okay, and we let go of the 2 ends of the wire, what's going to happen? The wire will go back to its original length or shape. Okay, so we want to stress materials out so that it stays inside its limit of proportionality. That means it can stretch and come back, and stretch and come back to its original shape as it works, as it carries the loads. Okay, so people, now, if I go back to that, so if we plot the force extension diagram, and we plot the stress strain diagram, we see that we get a diagram that looks like this, and this is called where's the name of the diagram? Let me just see. Yeah, anyway, this here is a stress strain diagram for a mild steel bar. Okay, stress strain diagram for a mild steel bar. So if we take a mild steel bar, piece of wire, and we stretch it out from north until it fails, and we plotted a diagram of stress against strain, does it look like there? Okay, now people, just very quickly, I'll talk about this more in lessons as I go. Here's a table, 3.2, it's called Approximate Mechanical Properties of Materials. Here we got a list of materials. The top one here is high strength steel, and we go down, and we go down to aerated concrete. Okay, now look at the first column here, it's called E. Okay, that E there actually stands for elastic, but more fully stands for Young's modulus of elasticity. Okay, and notice here the numbers there. It's 200 to 210 kilonewtons per millimeter squared. And generally, as we go down the list here, the numbers get smaller. Okay, so that means this material here, okay, is the strongest material, and this material at the bottom there is generally the weakest material. And by the way, what's aerated concrete? What the word aerated, anybody know what aerated means? Make it a bit bigger. Aerated means that when you make concrete, and as we pour concrete, or as we stir it, or as we place concrete, we introduce bubbles of air into it. Okay, it becomes, we say it's aerated. Okay, so I don't know, I'm sure you like chocolate. If you eat Aero, doubly bubbly chocolate, yummy. Okay, There's little bubbles in there. Now that's aerated chocolate. Now when you introduce bubbles of air into a liquidy material, it becomes aerated. As aerated concrete. Okay, so we aerate concrete to still keep its strength properties within a certain limit, but we make it a lot lighter because there's lots of gaps in there. Okay, but people, if you go to the top here, we'll see there that high strength steel is the strongest material there. And what is high strength steel? Okay, if you go to a building site or construction site where they're putting up a concrete structure, okay, very often inside the concrete there, we are not just going to have concrete, we're going to put steel bars inside there, okay? And that steel bars there is what you call high strength steel bars, and that's the bar over there. So if you go to a typical construction site, the strongest material on any construction site is most probably going to be your high strength or high yield steel bar, okay? And when we say a material is very strong, what are we saying about it, do you think? Which feature about it do you think we're talking about? We are talking about its tensile ability. That means its ability to resist tension, like we did to the wire here. Okay? So when we talk about a high yield strength bar, we say it's very strong. We're saying that it's got a very, very high resistance to being stretched or undergoing a tensile load. Okay, so people here, you can see here, so that means the higher the E value of a material, the stronger its resistance against stretching. Okay, so there's a G value, which we're not going to be concerned about all, and there's other bits over there, but the material there and its E value is the bits that's going to mainly concern us out of this table here. Okay, so people, that's a little bit of an introduction regarding stress and strain. If I just go back to I think that's all I want to say there. If I go back to my note over there, there's your stress strain diagram for a mild steel bar. There's a list of materials with the E values. We're going to talk more about it and use it in calculations in the next lesson. If I go up, there's some formula and there's bits there. There's the 4 pages there, and that's all I want to say as a way of introduction for stress and strain, and I will see you in the next lesson.